point B?
Ultimate strength.
Thank you. So point B is your ultimate strength. Okay. Why I'm saying this is, if we look at, can someone tell me, right, what is a factor? What is the formula for factor of safety? Anyone, please? What is the formula for factor of safety? Anyone? So can someone Google and let me know, please? What do we mean? How do you determine factor of safety? What divide by what? Anyone? I hope you guys can still hear me, right?
It's strength over stress.
What type of strength?
Maximum strength.
Huh? So is it yield or ultimate?
Ultimate.
Ultimate, right? So it is stress ultimate over stress
Design.
allowable. Okay, what you allow. So we're going to look at a textbook. Okay, so I'm going to refer to the, if I can find a textbook.
Eugene, in most cases, if you're beyond the yield strength, wouldn't your part have already failed? Not failed yet, but it won't be usable anymore.
What's your name?
Wait.
Wei. Yeah, you have a good point down there. But let's look at the textbook, okay?
Okay.
Wei, I did not say that you are wrong. Okay? I did not say that you are wrong. Don't say, okay, I'm wrong. No, you are not. Okay? I did not say that you are wrong. You are, in fact, partly right. Okay? So if we were to refer to the textbook, let's look at the textbook. Where is the textbook regarding factor of safety? Okay, here it is. Okay, can you see that? So the factor of safety, okay, is based on the ultimate strength or stress over allowable. Okay. So this is from the textbook. Exactly like how we have written. Okay, so you can refer this. Okay, this is textbook information. Right. Now, the textbook is not wrong. The textbook is right. Okay, but when is it right and when is it wrong? Right? Okay. Now, hear me out down here. Okay. We know that the ultimate strength, okay, we know stress, ultimate strength is greater than yield strength, right? We can see this trend, right? So the problem with this formula, equation number 1 we have written, okay, is only allowable to work for brittle material. So for brittle material, right, the factor of safety is equal to stress ultimate, or ultimate strength divided by stress allowable, okay, for brittle material. For ductile material, now why this is the case, okay, I'll tell you why later. But for ductile material, right, the factor of safety is equal to the yield strength divided by stress allowable. Okay. As we mentioned before, we want our stress state to be in the elastic region in structure design, right? That is why our factor of safety is based on the yield strength for ductile material. Now, can someone tell me why for brittle material you can use ultimate strength? Interesting, isn't it? Ductile material, you stop at what? The yield strength. For brittle material, you can use ultimate strength. Brittle material are like concrete, for example. Can someone tell me why, please? Anyone?
Is it because under tensile or compressive loads, the material can actually get stronger up until that point?
Now, for you are partly you're partly right. Okay, you are like 30% right. Okay, you're close.
That's like 70% wrong though.
Okay,
That's still like 70% wrong though.
no, you're partly right. Okay, not the for this answer is not the full answer. Anyone, please?
It's because the brittle material is very close to the yield and the ultimate strength. So it doesn't matter if you use one or the other.
Where are you? What's your name?
Patrick.
Patrick, you're absolutely right. So let me draw for you what Patrick have just said. Okay. So if now we have a stress strain curve again. Okay, I'm going to draw two curves. So this is our ductile material. And the next one is our brittle material. Right. So for ductile material, this is the yield strength. This is the ultimate strength. For brittle material, this is the yield strength, and just a bit higher, this is the ultimate strength. So what Patrick say is this, okay, Patrick, okay, correct me if I'm wrong. What Patrick mentioned is for brittle material, the ultimate strength is approximately equal to its yield strength. Very close, okay, not huge difference. This is exaggerated. In fact, okay, a lot of brittle material, once it reaches yield, okay, it will break. Okay, whereas for ductile material, the ultimate strength is usually greater than the yield strength. Okay, you understand now? Yes or no? Does it make sense now? Okay, not rocket science, is it? Okay, but it's just applying fundamentals. Ladies and gentlemen, this is what a university degree is all about, right? It's not just knowing the formula, right? Why you apply for one situation and not the other, and the operating boundary is the gist of understanding or understanding a topic taught at the university level. This is critical. Okay, when to apply what and why. Okay, right. So I hope it will inspire you more wanting to know more why a certain formula is this way and when to apply which formula and why. Okay, and that's critical. Any questions so far? No. Okay. So let's look at. So this is method number one, right? We find our reaction force, right? We find our reaction force. Then we do P divided by area, right? Then we calculate our stresses. Then we compare with the allowable or the maximum, okay? And then I just taught you what to use. Is it yield strength or ultimate strength? Okay, right. Now let's look at method number two now. Okay, method number two is based on elastic deformation. Okay, based on elastic. And I'll write out the formula for you first. Okay, then after writing out the formula, we see how the formula is derived. Okay, I'm not going into in-depth deriving. Okay, I'll make sure that when I derive, right, you can understand what I'm doing. Okay, we're not going to do too much integration or differentiation for now. Okay, that is later part of the course. So based on elastic deformation, we have deflection is equal to P L naught divided by A over E. And by now, some of you say, yeah, you have seen this formula before, yes or no? All right, you've probably seen this formula before, where deflection is equal to PL over AE. So I'm going to define over there. So delta is your deflection. Right, and deflection, because we're in Canada, is in meters or in inches. Okay, so P is the axial load. So it can be in Newton or it can be in pound force. Okay, and then L naught is the original length. Okay, again, meters or inches. And then A is the cross-sectional area. And this is in meters squared or inches squared. And then we have E, which is your Young's modulus. Which is in Pascal or pounds per square inch. Okay, so I'm going to give you some common Young's modulus. So if you have a material over here, these are the three usually used material. You have your steel, you have your brass, you have your aluminum, and the E value in terms of gigapascal. So as an engineer, you have to try to remember this. Okay, 110 gigapascal. So gigapascal is times 10 to the power of 9 in case some of you forget. Okay, Pascal. So these are the three commonly used material for structures. Okay, now, so how is this formula derived? Okay, it's good to understand sometimes, not always. Okay, it's good to understand how some formula is derived. Only if you understand how is it derived, then you will know the operating boundary. Okay, and I'll elaborate what do I mean by that. Okay, so as I mentioned before, for this week is under axial loading condition. Okay, so this formula can only be applied, okay, where delta is equal to PL naught over AE, can only apply under axial loading condition only. Okay, if there's bending, there's torsion, you cannot apply this formula anymore. Okay, so if we have a structure again, similar to what I've drawn earlier, right? So from here to here now, this is our L naught, okay, and then over here, this is our area, okay, and I'm going to sketch our neutral axis. Okay, so this is our neutral axis. Okay, so this is our neutral